Okay, sequences and series. I mean, this will seem like not like anything that you did before, right? It's different. You're probably thinking a positive way. Probably tired of all these X's and Y's and functions and domains and ranges and all that stuff. And after today we learn about the basics about sequences and series, and then the next two classes we learn about two particular kinds. And for those two particular kinds, we have formulas for everything we do. It's on the Algebra 2 formula sheet. Right? So mostly it's about if you've got a formula in front of you, can you use the formula? And in math and science, that's about as easy as it gets. If you've been given the formula, you should be able to learn how to use it. But I think that there's some of this stuff that just is sometimes conceptually just hard to wrap your brain around. But once you can get it, it shouldn't be that hard. So first we start with the sequence part, right? A sequence, by definition, is an ordered list of numbers. So, for example, and this was like a revelation in the last class, E dot G dot, that means for example, right? That's what that's for. What if I said I dot E dot? What does that stand for? It's like saying that is, right? It's Latin abbreviations. Not that I speak Latin, but EG is some ergo something, So that's an example of a sequence of numbers because it's three numbers, And order is important, right? It would be a different sequence if I changed the order of these three numbers, right? If I made it 45, 34, and 23, that's not the same sequence because I just changed the order. Right? Now, individual terms in a sequence are referred to by the lowercase letter a with a subscript, right? And the subscript denotes which number in the sequence that I would call the ordinal number of that term. So a sub 1 means first term, a sub 2 means second term, a sub 3 means third term. So A1 is 23 up here, A2 is 34, A3 is 45. Right, and these are, it doesn't quite look that way, the way it's written on the slide here. I was just using the font that was in there, but remember, that is a subscript. It's a little smaller and it's a little bit down. Don't write it like A1, like it's like you're multiplying A times 1. You're not. Okay. Okay, Emily? Don't do that again. Right. Sequences can be finite or infinite. Right. If you see a dot, dot, dot after that, it means it goes on. There's more to come, and it doesn't ever end. If that's infinite. If it's just so many terms, there's no dot, dot, dot at the end, you say that, you pronounce it as finite. Right? Finite and infinite. Okay, should be good. I skipped one. So sequences don't have to have a pattern, right? But if they do, then you should be able to come up with a formula that describes the pattern. Right? In this infinite sequence, 2, 4, 6, 8, dot, 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 right? A1 is 2, A2 is 4, A3 is 6, A4 is 8. What do you think A5 is going to be? 10, right? So if you can represent it with a formula, that formula is called the nth term of the sequence. And it's written like this, A sub n, right? And then you're going to write down what formula we have that we'd be able to plug in for n, 1, 2, 3, 4, and it would generate a formula that would give us these numbers. What do you think our formula should be that creates that sequence? 2n, right? So now, if I want to know what the first term is, that means I could substitute n equals 1. I would go 2 times 1 is 2. For A2, 2 times 2 is 4. So this is a general formula for one term in the sequence. Good. So if you have a general formula, then you don't have to keep adding 2 until you get to that number. You just plug in for n. Like if our formula is 2n, then how do I find the 10th term? I plug in n equals 10, right? And the answer is 2 times 10 equals 20. So it's kind of like using f of x, right? If I wanted to evaluate a function for a value of x, then I just plug in. Like if my formula is 2n, a sub n equals 2n, it's kind of like saying f of x equals 2x. In either case, if I want to know a2, a8, or f of 8, I plug into the formula. I get the same thing. It's 16. So you have to think of this formula for the nth term as kind of like function notation when we're using functions. The difference is that with a function with f of x, you could plug in anything for x, right? I can plug in the square root of 2 or 1.5 or whatever. If I'm using a sub n, the n is going to be some kind of a integer. Usually a counting number like 1, 2, 3, 4. You can't plug in decimals and irrational numbers here. But other than that, it's kind of like using f of x. Okay, we're good. Press. So if you have a formula, you should be able to generate terms in the sequence. This is a very common kind of question. Here's a formula for a sub n. Write the first 6 terms in the sequence. So that means plug in for n 6 times. Right? A1 will be 2 times 1 plus 5, which is 7. A2 equals 2 times 2 plus 5. A3 is 2 times 3 plus 5. A4, 2 times 4 plus 5, which is 13. A5, 2 times 5 plus 5. And A6, 2 times 6 plus 5. All right, so you should know how to use a formula by just plugging it in, calculate what you need. So try to write the first 6 terms of that sequence. -2 to the n minus 1. So notice the pattern, right? When you plug in n equals 2, then you're taking -2 to the first power, right? Which means it's going to be a negative number. But when you plug in n equals 3, now you're saying -2 to an even power, so that negative times negative makes positive. So it's going to alternate signs, which is common, right? It'll alternate signs. So it's 1, -2, 4, then what's the last 3? -8, A4, -8, A5, +16, A6, -32. You know, every time you increase n, that means you have one more factor of 2, so it doubles it. And then because of the minus sign, it's making an alternate sign every time. All right. So now we have to use a little imagination sometimes to try to think of what formula might have generated that sequence of numbers. Anybody? Looks like it's just the cubes, right? Except for one difference. They're all negative, right? Okay, so how would I write a formula for that? A sub n equals negative and cubed, right? I mean, does it matter whether I put that negative inside parentheses before I cube it? I mean, in the end, it doesn't matter because a cube of a negative is a negative and a cube of a positive is a positive. So it wouldn't make any difference. So, I mean, and usually when you're trying to come up with these formulas, if you make up the formula and you're not sure, then test it. You know, plug in the first few numbers and see whether it's generating the terms of the sequence you think. So if I put in a 1, 1 cubed is 1, -1. Put in a 2, 2 to the third is 8, -8. 3, -27. Okay, so it looks like it works. I mean, we don't really get too deep into this, but I've been in classes before, probably more like number theory kind of classes, where it's very hard to come up with the right formula, and you do have to test it out. You know, you come, oh, I think I got it, and then you try it out. It's like, that one didn't work. You try it again. Most of these you could get without too much trouble. Okay, what would be the pattern? What would be a rule, a formula that would generate those numbers? Okay, I thought maybe you were. Not an obvious one, definitely. Anybody? Usually when I'm looking at them and I'm a little, because I think that a lot of times we're kind of stuck in linear mode. And so sometimes you need to be thinking of squares and cubes and things like that. And I looked at that, I said, well, will that work? 1 squared, 2 squared, 3 squared? Not exactly. What adjustment could I make? Let's see, if I did 1 squared and generated a 0, yeah. Okay, well, then 2 squared plus 2 would have been 6. That's not right. And 3 squared plus 2, yeah. Go ahead. Subtract the 2, right? So it's like n squared minus n, right? 1 squared minus 1, 2 squared minus 2, 3 squared minus 3. That looks like it'll generate it, right? So a sub n equals n squared minus n. Now, in the book, that's not what they had. They said it was n times n minus 1, which is just the factored form of the same thing. But now what you're saying is it'll be whatever that number is times the number 1 less than that, right? So this is 1 times 0. This is 2 times 1. This is 3 times 2, right? So you've got to be a little creative sometimes to think of these things. I mean, they said in the directions here, write the next term and then find the rule. Well, I don't know how you would have found the next term if you didn't have the rule, right? What would be the next term in this sequence? The 1, 2, 3, 4, fifth term. I think it would have been 20. Right? A5 is 20. A5 equals 5 times 4, which is 20. Okay, that is the what is a sequence part. Now we get to the what is a series part. A series is the sum of a sequence. Right? The sequence 23, 34, 45, if I replace all those commas with plus signs, that's a series. We're going to add them up. Right? And if the question is, here's a sequence, write the series, what they mean is, show this sum, right? If they say evaluate the series, that means actually add them up, right? So turning a sequence into a series does not imply that you just added them up. So you need to show the pluses and everything. Otherwise, if I said, write the series and you just gave me 102, you didn't really do what I asked, you know what I mean? So write the series, this plus this plus this. So this is not a long lesson. We'll be done plenty of time. Good. Now a series, just like a sequence, could be finite, it could be infinite. Right? A finite series just means you're adding up a fixed number of terms. An infinite series means you're adding up an infinite number of terms. No, in either case, sequence or series, the infinite is represented by the dot, dot, dot. Yeah. Really good question. How do you add up an infinite series? You can't always, okay? But we will, not this lesson, not next lesson, but in 2 lessons we will. Here's a series to try to imagine the series, okay? I'm going to add up an infinite number of terms and you'll see that I can add it up. Imagine that the length in some metric from this side of the screen to the other side of the screen is 1, okay? And I am going to walk from this side to that side, every step going halfway to the end, right? After the first step, I'm right in the middle. After this step, I'm halfway there. I'm halfway there. I'm halfway there. I can go on forever, right? I'm never going to get to the end of this screen. So you would say that that series is converging to 1. Kind of like a graph of a line approaches an asymptote. You know, it gets infinitely close. It really doesn't quite get there. But in terms of the series, you would say it's converging to 1. And we will do those, not next lesson, but the one after. You can't add up this kind of a series because in the end, every time you add one more number, you just change the sum. So there's no way to do that. But there are conditions when you can add them up. And it's actually what is important about this kind of stuff. And I'd actually never realized a lot of the implications of this stuff I mean, I've taught this in Algebra 2 for years with the amount, and pre-calculus, what you guys call math analysis here. And we just kind of like skim along the surface with this stuff. But I read this book, I probably told you about it earlier this year. It's called The Grapes of Math. And he really showed some things that you do with these infinite series like that, and showing how they converge. That it's almost, I don't know, it's like we've already dealt with things like e, the base of the natural logarithms. We've dealt with I, which is the definition of the square root of -1. We will get to things like sines and cosines and things like that. And it's through these kinds of infinite series that they all kind of like become the same thing. You know, there is a formula, an equation, which is this: e to the I pi plus 1 equals 0. So just think, you know, 1 is like the most important number of all, right? 1. It's where everything starts. It's counting numbers, everything. E, the base of natural logarithms. I, pi, you know, and somehow they all add together and give you 0. I mean, how does that happen? It happens through these kinds of things. Through these kinds of things, and another thing, which you may or may not have seen before, which we think we talk about a little bit, but not until the end of the course, called factorials. Factorials are like 5 factorial is 5 times 4 times 3 times 2 times 1. It's whatever that number is times every number less than it until you get to 1. So when you get infinite series of factorials, it actually makes all this stuff like come together to where you can have an equation like that. And I'd never seen that myself. But I think it's fascinating how they might be the same. At some level, they're the same. Okay, if that's all we were doing with series, you'd say that's not hard. But where I think it usually gets a little more complex conceptually, is we start using this notation, which is either called summation notation or sigma notation. And the reason it's called sigma notation is because that's the Greek letter sigma. It's the capital Greek letter sigma, right? There's another one which we'll use later to represent standard deviation, which is the lowercase letter sigma, but that's a capital sigma. And I'm going to write it in there now like that, but you know, most of the time, we're not taking that much time to draw such a careful symbol. I mean, most of the time, if I have to make this symbol just because I'm working out a problem, it's going to look something like an E. Maybe it'll look a little better than that. Right? Something like that. Maybe it's an E, maybe it's a backwards 3, something like that. Okay. Now notice the things that go around the E, the sigma. Underneath, yeah, and actually this was a mistake. That should be an I. In fact, I think what I'll do is like this. In front of the sigma, there's going to be a formula for the nth term of a sequence. Now, whether you use n or I or k, it doesn't matter, right? There could be anything there. But this number here, this letter, whatever you use for it, that's called the index of the summation. So whatever that is, that's the letter that you're going to see in your formula. Okay. And this is telling you to start counting at 1, and you're going to keep plugging into this formula, increasing by 1 every time until you get to whatever number is on the top here. So this is the lower limit, this is the upper limit. This is the index, this is the formula for an. So for example, in this formula here, before I start doing this part here, what is the formula that would generate these terms of a sequence? 1, 3, 5, 7, 9. Try to imagine the formula that would generate 1, 3, 5, 7, 9. Okay? Think. Say again? 2n minus 1, right? 2n minus 1, so 2 times 1 minus 1 is 1. 2 times 2 minus 1 is 3. 2 times 3 minus 1 is 5. Good. So the formula is 2n minus 1. Now, since I used n in the formula, I've got to use n as the index. And now I want to have a lower limit and an upper limit that will make me plug into that formula how many times? 1, 2, 3, 4, 5. So simplest way to do this is let's just let the index go from 1 to 5. So the way you use a summation notation is first you plug in the lower limit. 2 times 1 minus 1 is 1. Okay, then you put a plus sign and you add 1. 2 times 2 minus 1 is 3. Plus, add 1. 2 times 3 minus 1, 5. Right? And you keep going until you get to the number on top. The last term will be 2 times 5 minus 1, 9. So this is the same as this. Yeah. No, the lower limit is the first number you plug into this formula. It's just a coincidence this time that actually this one and that one are the same. It doesn't have to be. And then this, the upper limit is the last number you plug in. So 2 times 5 minus 1 is 9. You get it? Okay, so this was a finite series because there was only 5 terms, and that's sigma, looks good, right? How do you think it would change if it was an infinite series? Okay, so what do you think is going to go on top of the sigma? The infinity symbol, right? So if I make it like this, n equals 1 to infinity 2n minus 1. There you go. And we've already used the infinity symbol, right? And people aren't confused about that. Right? We did that with our n behaviors at the very least. I've taught this before where kids were not aware of that symbol. You said, why are you putting an 8 on the top? Lazy 8 is laying down. Are we good? Okay, Michelle? Don't be shy. If anybody has a question, probably somebody else has the same question. Okay, so let's come up with let's represent that series with summation notation. So first thing, let me draw my E, my sigma. What would be a formula that I could use to generate these terms? 25, 50, 75, all the way up to 250. What would be the formula? 25n, right? 25 times n. Okay, now since I used n, then n is my index. And basically at that point, I know what is going to be the lower limit. Since the first term is 25, it's going to have to be 1. Okay. And now this one, it did not tell you how many terms, but just looking at the values here, it should be 10. Because you could tell that when you plug in 10 times 25, you would get the 250. Right, so that what goes in front of the sigma is the formula for the nth term of these numbers. Right? And then this is a counter. I always think of it like a counter, that's just counting off how many terms that there are in between here and here, and it should generate all of those. Okay. What's the formula for what you're looking at there. N over n plus 1, right? So he separated the numerator and the denominator, right? If all you had to do was generate 1, 2, 3, 4, so it's n. If it's 2, 3, 4, 5, okay, it's n plus 1. So just split it up. N over n plus 1. N equals, what will be the lower limit will be 1. And then because of this, you got an infinity on the top. So the sum from 1 to infinity of n over n plus 1. Good. Okay. Next. So you try this one. Try to come up with the summation notation for that. What's the formula? 6n. I mean, this is 6 squared. This is 6 to the third. So it's 6 to the n, right? Not 6 times n. That would give you 6, 12, 18, etc. And then n equals 1 to infinity. All right, try this one. So what was your formula that would make those numbers? N plus 4, right? And so the counter goes from 1 to 8. So infinity standing up now. Okay, now, honestly, that's not always the way you would write that, because you don't have to start at n equals 1. You can write the summation. I could have generated the same terms by going n equals 5 to 12 of n. Right, so the first number, I'll plug in the lower limit first. The first term will be 5, and then 6, and then 7, then all the way up to 12. So you won't, every summation will not start at 1. And when we get to the next lesson, sometimes you're asked for how many terms are you adding. And so it's different if you're looking at a summation and it doesn't start at 1. It's easy when it starts at 1, you always say, okay, it's 8. It's whatever the number is on top. That's how many terms I'm adding up. When it starts at 5 and ends at 12, your instinct is going to be to subtract 12 minus 5. But how many terms that would only be 7. So it's always 1 more than you would get if you subtract. I mean, even here, right? 8 minus 1 is only 7. But there's clearly 8 terms being generated here. So be careful if the index doesn't start at 1, because the number of terms is not going to be just that minus that. It's particularly not going to be the top number anymore. That's probably the number one mistake, is you're looking at that, say, how many terms is it? You say 12. No, because it didn't start at 1. So you got to think this a little bit more. Okay. So with that admonition, let's add up this series. So how many terms am I going to be adding up here? 5, right? Starting at 4, ending at 8, you've got 8 minus 4 plus 1, it's going to be 5, right? And the only way I've got to do this at this point is I'm going to have to plug in 4 and then 5 and then 6 and then 7 and then 8. Let's see what that looks like, right? That'll be 3 plus 4 squared plus 3 plus 5 squared plus 3 plus 6 squared plus 3 plus 7 squared plus 3 plus 8 squared. Which is 5 times 3, right? There's a 3 in every one of those. And then it'll be the plus 16 plus 25 plus 36 plus 49 plus 64. Okay, and you can add up all those, and they equal 205. Especially if you've got a funny formula there, then there's really nothing else you can do except generate the terms and add them up, see what you get. In the next couple of lessons, I could say we'll be getting formulas for doing summations for particular kinds of sequences, but this is not one of those. $41, $77, and $30, and $23. That doesn't seem right. Okay. So we good with that? So now, after we finish with that, I'm going to show you actually how you can do that in the calculator. Ready? 1, 2, 3, go. So here's how you do the same thing with the calculator. And I'm going to guess that because other people were using your calculator last class, that it could actually be already set in a different way. Clear. I mean, if you go to the main screen on your calculator right now, hit the X button. What do you see? Just hit the button, this one right here. What do you see on the screen? Does it say X? For some people, it may be N, right? So, in fact, you don't need to change this. You don't need to change the mode to do what we're about to do right now. But the fact is that the calculator has a particular mode for sequences. If you see the mode key, which is to the right of the blue second key, click on the mode, and if you go down to the 4th line, all the way to the right, it says SEQ for sequence. Okay, usually it's in the first column, FUNC for function. So you can set it to sequence by move the cursor over sequence and hit enter. And then when you go to the main screen and you hit the button that we usually hit to get an X, you get an N instead. In fact, go to the Y equals and see what that looks like with the mode for sequence. It's not the same anymore, right? It changes everything. Now, we don't need to do that. In fact, I almost never use this mode. It confuses me more than anything. I'd just rather use X and be done with it, but it's in there. And the other thing is, if you notice now on that key that you usually hit for X, notice that there's actually 4 letters on there. There's not just one. The first one is X and the last one is N, but there's 2 others for those other 2 options in that row, polar and parametric. So you can change and see how it changes what you're looking at on the screen by changing into those modes. In this class, we don't use those. In math analysis, you use those. But this is what you need to know. Again, whether or not you change the mode or not, you can still do this, right? Hit the math button from the main screen. Just hit the math button and then scroll all the way to the bottom to the 0, and there it says summation. You see that? So go up to the 0 or just hit 0, and it'll bring up that summation notation. So if we want to do this one, k equals 4 to 8 of 3 plus k squared, then hit the X button. In my case, it's bringing up an N. Then I do 4. Then I right arrow to get to the top of the sigma, and I put in 8. And then I go inside the parentheses, and I put 3 plus n squared. 3 plus n squared. And get out of that. So does that look the same? So when I hit enter, it does it for me. Yes. But there will be some that are not given to you in series form, or in a sigma form, so you won't be able to use it. But there'll be some that you can. Now, there's another place you can find the summation notation in the calculator, and it's kind of a convenient place for it too. If you hit the alpha, the green button, and then the window, alpha, window, it brings up a few functions that are often used. So the first one is absolute value, the second one is the summation, and the fifth is the log of any base. So that's another place you can find it. But it's in the math menu. If you can't remember, go to the math menu. Okay. So do this last one. Use the calculator by all means. Find the sum. I equals 3 to 7 of I squared minus 1. So let me do it. Alpha, window, 2. And I'm going to go n equals 3, 2, 7. And I'll put in n squared minus 1. Enter. 130. So we all get 130? Anybody need help with that? Just seeing how to do that? Okay. So this one was 130. And that's it. Those are the basics of sequences and series. And that's the homework.